Hello everyone, I'm Dheeraj Madan. Welcome to this new video. So recently the election season has just gotten over in India, and during the vote counting process we witnessed a sort of a close competition between the two major groups who were contesting for this election in India. And some of you might be wondering that what if the winning party maintains a lead throughout the vote counting process itself, right? So is it possible? What are the chances of that? And that is something which we are going to look at today. So this question was initially answered by someone called Bertrand in 1887, and we are going to look at that result. So it will be a sort of an interesting question which we are now looking at. So let me just first directly state what is the problem I'm talking about. So let's say that in an election with two candidates, A and B, who receive P and Q votes respectively, what is the probability? And let's say P is greater than Q. What is the probability that A strictly maintains a lead over B throughout the counting process? So here we are assuming that the votes are uniformly shuffled. So before we begin the counting process, we have uniformly shuffled all the votes, and then we begin the counting process. So here we are looking at computing the probability that A maintains a lead, strictly maintains a lead over B. So what do we maintain? What do we mean by maintaining by strictly maintaining a lead, right? So what we mean is that at any stage during the counting process, the number of votes received for A is strictly higher than the number of votes for B. So let us take some scenarios. Let's take some examples and see what is the event for which we are trying to compute the probability. So let us take some examples. So let's assume that P is 3 and Q is 2, meaning that there are 3 votes which have been casted for candidate A and 2 votes casted for candidate B. So what are some of the sequences which are possible over here? So we can have, for example, all 3 votes for A followed by 2 votes for B. We can have 2 votes for B followed by 3 votes for A. We can have something interleaving, for example AA BB A, or maybe BB, let's say AB AB A. Right, so these are some of the sequences which I'm just writing down. So let's look at the first sequence, which consists of 3 A's followed by 2 B's. So as we begin the counting process, we see 1 vote for A, right? So until now there is 1 vote for A and 0 for B. I receive another vote for A, which means that now the tally has 2 votes for A and 0 for B. And then I have 3 votes for A, 0 for B, and then 3 votes for A, 1 for B, and then 3 votes for A, 2 for B. So we see that throughout the counting process, the number of votes for A is strictly higher than the number of votes for B. So this qualifies as a valid sequence, right? Or this is something I'm going to call as a good sequence. Another example is when we have 2 votes for B followed by 3 votes for A, right? So here we see that right in the first vote itself we have a right in the first vote itself we have a vote for B with 0 votes for A, right? So this is a bad sequence because here the winning candidate has lost the lead in the first vote itself, right? So this is a bad sequence. So by good and bad I mean, good sequences is the which are belong to the event set for which I'm trying to compute the probability. If I have something like AABBA, right? So initially the tally is 1 0, then the tally is 2 0, then tally is 2 1, and then at this vote, right, when I have received 2 for A and 2 for B, the tally is 2 2, right? So it's almost like a tie, and then finally A wins, right? But since here A is not strictly leading, right, after the fourth vote, I'm still going to call it a bad sequence, right? Because what I would want for a good sequence is that A should maintain a lead strictly throughout the process. So in the last one we see one vote for A, 0 for B, followed by 1 vote for A, 1 for B, right? So as soon as I get 1 1, it means that it is a bad sequence, right? Because A is not maintaining a lead right now, right? Because after the second vote it looks like a tie after the second vote, right? So I would not call it a good sequence. So we need to compute the probability of good sequences. So how do we do that? Right? So there are lots of ways to actually compute the result. We are going to look at the process in a combinatorial manner, right? So before I start describing the solution, let me tell you the answer itself. So the answer is that this probability is P minus Q over P plus Q. So how do we compute this? So as I just mentioned, we are going to look at this combinatorially. So let's try to do that. So the idea is that, so what is the total number of sequences with PAs and QBs? So how many are the such sequences? So if I consider interleaved sequences of A's and B's where there are P plus Q total number of elements, and and P of these elements have an A and Q of them have a B, then essentially the number of such sequences is going to be P plus Q choose P, right? Why? Because amongst the P plus Q positions I need to choose P positions where I'm going to place a P. I need to choose P such positions where I'm going to place an A, and the remaining will be filled by B. Right, so out of P plus Q positions, I choose P positions where I place an A, and remaining are filled with B. So the number of such sequences is P plus Q choose P. Now, I need to count the number of good sequences, right? The number of sequences where A strictly maintains a lead over B at every position. So how do I do that? Well, maybe it's easy to do the reverse. So let me compute the number of good sequences as total number of sequences minus the number of bad sequences. So how do I compute the number of bad sequences? Well, one thing is clear, that if the first vote itself is for candidate B, it is a bad sequence, right? Because over there candidate B has taken the lead right in the first vote itself. Okay. So what I'm going to do is that I'm going to divide the number of bad sequences as those which with a B in first vote and the number of bad sequences with an A in first vote. So it's probably easy to count the number of bad sequences with B in the first vote, because all such sequences with B in the first vote happen to be a bad sequence, right? So number of bad sequences with B in first vote equals number of sequences with B in first vote. And how many such sequences are there? Well, there are a total of like P plus Q votes, out of which the first one is fixed to be B, which means that out of the remaining P plus Q minus 1, I need to choose P positions for A and Q minus 1 for B. So if I fix positions for A, then positions for B are automatically determined. So I can write it as P plus Q minus 1 choose P, or equivalently P plus Q minus 1 choose Q minus 1 also, right? Because there are P plus Q minus 1 remaining positions to be filled, out of which I need to choose the P positions where I'm going to place an A. Similarly, I can also consider choosing the Q minus 1 positions where I need to place the remaining number of B's. They are essentially equal only, but okay, let me just write it as P plus Q minus 1 choose P. Now coming to the tricky part. So what is the number of bad sequences with A in first vote? Right. So this is now the tricky part, and the answer is that this equals the number of bad sequences with B in first vote, right? So you might be wondering, well, why are these two quantities equal, right? Because when you begin with A, then there are so many other things you need to take care of, right? For example, A followed by a B will be a bad sequence. If you have two A's, then maybe at some point there might be a tie. So it's very difficult to count the number of bad sequences which have an A in the first vote. But then I'm claiming that these two are equal, the number of bad sequences with A in the first vote and versus the number of bad sequences with B in the first vote. So how do I show that these two quantities are equal? Okay, so this is a tricky exercise. So how do we do this? Well, the idea is as follows. Let us represent this vote counting process in the form of a grid. Okay, so let's say I start from origin, and on x-axis I count the number of votes for A, and on y-axis I count the number of votes for B. So for example, if I have a sequence as 3 A's followed by 2 B's, what I'm going to do is that as soon as I receive an A, I move one step to the right, and in my vote counting process, I have 1 vote for A and I have 0 votes for B. As soon as I receive another A, I move again one step to the right, and I have 2 votes for A and 0 votes for B. As soon as I receive the third vote, I move again, take a one horizontal step to the right, and I am at 3, 0. Now when I receive a vote for B, I am going to reach 3, 1, which means that I have 3 votes for A and 1 for B. And finally, as I receive the next B, I have reached 3, 2, which is 3 votes for A and 2 for B. So I start from origin. Whenever I receive a vote for A, I move one step to the right. Whenever I receive a vote for B, I move one step upwards, right? So in general, if there are P votes for A and Q votes for B, so I need to start from origin and I need to reach the point P, Q by taking right steps and upward steps. Now what would be an example of a good sequence? So good sequence is one which always remains below the x equals y line, right? Because here x-axis is always greater than, so basically if x coordinate is always strictly greater than y coordinate, which means that I'm going to lie below the x equals y line, right? I'm not going to even touch this line. So I need to count these number of sequences. The bad sequences are those which touch the line or cross the line at some point. Okay. Now let's say that I have I have a B vote right in the beginning itself, which means that I have moved above the line right in the first vote. And since P comma Q right lies below this x equals y line, so at some stage in the vote counting process, okay, maybe in the first vote or second vote or third vote, at some point I'm actually going to cross this line, right? Because the reason is that since I have begun above the line, and in the end I should end below the line, I need to cross this x equals y line. So if we have a first vote for B, then we are going to cross the line at some point. Now what are the examples of bad sequences which begin with an A? So a bad sequence, if it begins with an A, then essentially I begin somewhere below this line, but then somewhere in the process I'm going to either touch the line or I'm going to cross the line. Okay, so the moment I touch the line, that means that there has been a tie. If I cross the line, that means that number of votes for B has exceeded. So I need to count the number of such sequences, the number of such paths from 0, 0 to P, Q, which start with somewhere below the line, but then either touch the line or cross the line at some point. So how many such sequences are there? And what I'm going to do is that I'm going to establish a one-to-one correspondence between the bad sequences which begin with an A, that is the sequences which touch the line and they start with and they start below the line, and the sequences which start above this line, which means that they start with a vertical step and they cross the line. So if they start with a vertical step, they'll definitely have to cross this line, because in the end P comma Q lies below the line. So how do I show this one-to-one correspondence? Well, what we can do is as follows, is that let's say you have some sequences which starts with an A and it touches the line, touches x equals y line at some point. So what I'm going to do is that I can reflect the path before it touches the line for the first time. So let me consider the path. So the idea is that we are trying to develop a one-to-one correspondence between bad sequences that start with A and bad sequences that start with B. So bad sequences which start with B are essentially all the sequences which start with B. So how do I develop a one-to-one correspondence? Well, I'm going to look at paths of these sequences. So any bad sequence which starts with an A starts with a horizontal line but touches x equals y at some point. Any bad sequence which starts with a B essentially starts with a vertical line and it has to cross this x equals y line because P comma Q lies below this line. So what is a one-to-one correspondence between these sequences? Well, if I start with a bad sequence which starts with an A, then essentially I reflect the part of this path before it touches the x equals y line for the first time. So let's just reflect this path. That will give me a bad sequence which starts with a B. So the idea is that I define this map from the set of bad sequences that start from A to the set of bad sequences or set of sequences that start from B as follows, is that I consider the path of the sequence which starts from A. Since it's a bad sequence, it touches x equals y line. I reflect the part of the path which touches this line and I keep the remaining path as it is. So essentially what I'm going to do is that, so this path I'm going to reflect about x equals y line and then I continue the path as it is. So if this particular sequence, for example, here was A, B, A, B, A, then I'm going to have B, A, B, B, BA, right? And essentially we can check that, you know, the later path which I get will be definitely be a sequence which starts from B, because, you know, once I reflect the path, then I'm interchanging all A's and B's. And also, since the part of this path was the one which was touching x equals y line, which means that until this path, until this part, the number of A's and B's are equal. So even if I flip, the total number of A's and B's are going to remain the same. So essentially this mapping will be a valid mapping. Okay, so this will give me a valid sort of sequence which starts from B. But now my claim is that this map is 1, 1 and on 2, right? Why is it 1, 1? Well, the idea is that, so what you can do is that, you know, if you reflect the second path, you know, you can actually recover the first path back. So basically, you know, if I reflect this reflected path again about the first time it touches x equals y line, I can recover my original path back, right? So essentially, if there are two sequences which map to the same path under the function f, then essentially their inverses are also going to be the same. So this is essentially 1, 1. And similarly, this is on 2 as well, because for every path in the for every you know, bad sequence which starts from B, I can find an appropriate sequence which starts from A, you know, by just reflecting this about x equals y line. So this is essentially an invertible mapping, and the inverse is also the same, that, you know, you again reflect the part which touches x equals y for the first time, and then about that axis only, and then you can recover your inverse as well. So essentially f is 1, 1 and on 2, which mean that you know, these two sets are of the same size, and the size of the second set we know is p plus q minus 1 choose p, which means that size of the first set is also p plus q minus 1 choose p. So therefore this is also going to be p plus q minus 1 choose p, right? And that means that number of bad sequences, total number of bad sequences, is going to be twice of p plus q minus 1 choose p, which means that number of good sequences is going to be p plus q choose p minus twice of p plus q minus 1 choose p. So therefore probability of a good sequence is nothing but p plus q choose p minus twice of p plus q minus 1 choose p over p plus q choose p, right? So this is 1 minus twice of p plus q minus 1 choose p over p plus q choose p. And essentially, if you now try to compute this, you have p plus q minus 1 factorial over p factorial q minus 1 factorial over p plus q factorial over p factorial q factorial, right? And essentially what would happen is that in the denominator only p plus q will remain amongst p plus q factorial term, because it will be, the remaining terms will be cancelled by p plus q minus 1 factorial, and p factorial is also getting cancelled, and in the numerator you will get q again, right? Because q factorial comes in the numerator and q minus 1 factorial is getting cancelled. So overall I am going to get p minus q over p plus q. So this is essentially an interesting proof, you know, with an interesting you know, geometrical insight as well. Hope you liked it. Yeah, and so that's it for today. Okay, thanks. Bye.